All right, we need to continue some boring, sort of complicated type of calculations today. Whatever it is with regression, we're going to be done this week, and next week we're going to start on complete different direction with Monte Carlo methods. So, just bear with me at least for today and tomorrow. So if you remember, we had a prior for the regression coefficients and sigma square that was slightly different from what you see here. There was an M matrix here, and this was an inverse gamma distribution. And I think I saw you through tables computed by the prior we considered on Tuesday, that when you were playing with that constant C, the results were very sensitive. Okay? So in some sense, this prior was extremely sort of damaging in case you don't have a lot of data. Okay, so towards sort of getting some informative prior, the first thing we will do is we will introduce this Zellner's informative G prior, still informative, and the only difference here is that matrix M is X transpose X. Okay, X, I remind you, is the design matrix that consists, each row is one data point consisting of the values of the input variables, the first column being 1. I still maintain the constant C there, but I also make the sigma squared to follow an improper prior, Jeffreys prior, basically 1 over sigma squared. So effectively, whatever formulas we derived last time for the general case, you can apply them directly to this case where you substitute this to be your M matrix, and you have to apply an informative version for sigma squared. So let's see what the results are going to look like, and if they're going to make any difference. So I remind you that the weird thing here is that the input depends on the data. The prior depends on the data, but only the input x coordinates of the data, all right, not the responses. All right, so it's unusual to use a prior that depends in any form on the data, but this is what we have right now. Okay, so the calculations are the same. You actually don't have to repeat them. You can apply the previous formulas, but I am going to do them very rapidly so you can remember what's going on. So effectively, to get the posterior of beta and sigma squared, you multiply the likelihood. This is the likelihood there. This whole thing is the likelihood, okay? Remind me, what is beta hat? The what? The MLE estimate. And the curly B here is the mean of the prior. Okay? All right, so, this comes from the prior in sigma squared, that is 1 over sigma squared. So apart from that, actually all the other terms are the same except this term here. Okay? And so I'm going to be giving you some of the results you can get basically by manipulating this. One of them, very important, is the conditional of beta of the coefficients given sigma squared. Okay, this is the posterior. So it looks nicely like that. And from this equation, actually looking at the mean, you can appreciate the nice impact of this prior, this Zellner prior that we use, because now you can see that somehow C defines the mean of beta as a weighted average of the prior mean and the MLE estimate. Okay, so in some sense, we will see actually later on, putting different values in C will be equivalent to certain percentage of the information you get from your training data. And obviously, the variance is also simplified because that M matrix is now X transpose X, so you get a nice formula. All right? Exactly as before, you can show that the sigma square, the posterior follows an inverse gamma. So if you need the posterior mean, is given by this nice formula. There is absolutely no magic on any of these derivations. It's just a few lines, but you know, if you don't do them carefully, and instead of n minus 2, you have n minus 25, you're going to be in trouble. Instead of c plus 1, if you don't have anything, you'll be in trouble. So you have to follow the algebra very closely. And I remind you, s squared, I don't know if we had it somewhere. Somebody remembers what's s squared? This is s squared here, right? It is basically the square error, but in your predictions, you use the MLE estimate. Okay? That's so something we know. All right. You can, if you go back to the joint posterior of beta and sigma square, you can actually integrate sigma square out, and you can come up with the actual posterior for beta that, not surprisingly, is a student t distribution, and it looks like this. Okay? So that's why I emphasize early on, right, when you take you know, Gaussians and you mix them together by summing for all possible sigma squares or all possible precisions, the result is a student t distribution. So this is how the student t distribution looks like. This is the expectation of the posterior beta. This is the variance, okay? And again, once you have these formulas, they're one line in your computer program. So I'm rewriting here the posterior mean of beta, and it looks like that. So you can see immediately if c equal to 1, the posterior mean is basically 1/2 of the prior mean and the MLE estimate, which means when c equal to 1, effectively the effect of the prior is equivalent to all the information you get from your data set. So really, this is a very strong prior. All right? And the question, of course, will be, well, you know, isn't this too much for a prior? What is the effect of C in the calculations? And we will see that there is an effect of C still remaining there, and maybe we need to do some modifications that we will discuss today. All right. This is the posterior of sigma squared, the expectation of sigma squared, the posterior. And so the tables you guys are going to be getting, using these formulas, they're already programmed for you. You can see for the different betas, this is the posterior mean values, this is the variance, and this is the Bayes factors. And I will do the calculation of the Bayes factors today, so you see from where the formulas are coming. But effectively, each of these numbers compares the marginal likelihood of the model where you include all the variables versus the model where you have excluded, you have removed, let's say, the intercept or variable 1 or variable 2. Right? So you're asking, do I need variable 1 or not? So you compute the Bayes factor keeping variable 1 and everything else, and versus the model where you keep everything but variable 1. All right? Of course, how do you compute the marginal likelihood in that case, or you know, for the full model? So that's something I'm going to show you today. So from this, you know, that's another way to say, you know what? I really need the intercept in the model. Variable 1 is extremely important. Variable 2 is very important. Then 5 and 6, but you notice here, I'm sorry, 4 and 5, but variable 3, not as important, okay? And various tables and calculations you will do, you will see that the point that this variable 3 is not very important. By the way, we did not numerate these variables in order of importance, right? So when somebody throws at you 50 inputs, you're not going to say, oh, this is more important than that and less important. You never know, all right? So you have to do this sort of analysis to figure out what is important and what is not. So what's the effect of C, right? So this is for values of C equal to 100. So this is what you get. So that, you know, you can remember some numbers here, 10, 6, and 2. 10, 6, and 2. So the Bayes factor has changed a little bit. You know, so when you go to C equal 1,000, the effect of C is a little bit less significant than in the prior we considered on Tuesday, but still, you know, there is an effect here. So you can see, for example, these when you calculate the Bayes factors, this for variables 4 and 5 can become very small, okay, versus what we had here. So there must be an effect, and certainly an effect on calculating the marginal likelihood. All right. So I need to show you, so we can finish with this particular prior, on how do you do predictions now, and we already have discussed this. It's similar to what we did on Tuesday. So basically now we would like to know, once we train the model, so these are the Y and capital X are training data, we want for any arbitrary set of inputs to predict what the probability of the outputs Y, this curly Y is. And effectively to do this, what you need to do is, right, you need to, bringing sigma squared here, all right? So you basically have to calculate the likelihood of Y squared, given sigma squared, times the posterior of sigma squared, okay? So you have to do this integral. And, you know, we already have done this, okay? So I'm gonna give you basically what the answers are. You can, to calculate this, looks complicated, all right? But if you condition things on beta, all right, you can use the trick that we discussed last week. So can somebody remind me what's the trick here? So for example, here the idea is, right, this distribution is a Gaussian. So it may be, rather than doing this integral, maybe it's okay to find the mean and the variance of this Gaussian. So how do we do that? So how do we find, you know, the mean of this distribution of curly Y given sigma square, the training data, and X curly? What was the idea here? To find the expectation of anything, you can do what? What happens if you know, if you can compute the expectation of the conditional distribution? So what you do here is you compute the expectation of the conditional beta distribution, and then the remaining result you take expectations with respect to what? To beta, okay? So, and the notation, you have to do it very carefully, right? Because you notice everything you do is conditioned on this, so you have to carry this thing. And when you take this conditional, obviously it will be conditional beta and everything else. So I'm writing it twice to emphasize that that is the case. And why is this easy? Because, you know, the conditional, the distribution of Y curl, if I know beta, then you know what this expectation is X curl times beta for my likelihood model, if I knew the parameters, okay? And then effectively what you need to do is from this will be these new inputs times the expectation of beta given that, okay? And that I already showed you the result before, all right? That it was this nice formula. All right, so in any event, this distribution here is a Gaussian, okay? We know this distribution being an inverse gamma, so no surprise, you can calculate the variance of the same thing. At the end of the day, the answer is a student t distribution. So the coefficients, basically the marginal distribution of coefficients follows a student t distribution. Okay, and so this, what you see here is I'm writing this student t distribution for separately for each coefficient. Everything is defined here. Omega I is basically the diagonal I element of X transpose X inverse. You know, these are the I values of the I component of the prior mean and the MLE estimate, and everything is known here. Okay, so from this, actually, what you can do, if you can normalize the variables, all right, you can get high probability density intervals, okay? So basically you can say, what is the interval where 95% of the mass of the coefficient, let's say beta I, lies, okay? And the same thing you do it with Gaussians. This high probability density interval, okay, looks like this, okay, where this function f is the CDF of the student t distribution. So effectively, if you want to calculate the region from A to B where let's say 95%, so if you make alpha to be 0.05, so you want 95% of the mass to be, this is the interval, okay? And this is basically the same way that you calculate confidence intervals with Gaussians. You can do the same thing with student t, but remember, this calculation here is a Bayesian calculation. This interval is not necessarily a centralized interval in general. So it requires sort of a little bit of more tricky work in general to compute if you have a non-symmetric type of distribution. So this interval, the way it is now, right, can be extremely useful for model selection. Can you tell me how? So suppose I calculate, let's say, for parameter beta 1, and I tell you the interval is from 0.5 to 0.25. What can you tell me about beta 1? Is beta 1 an important variable to include in the model if this interval goes, let's say, from 0.1 to 0.55 or something? How are you going to use this to do model selection as a new way for looking at model selection? When do you think there is a probability or significant chance that, let's say, the parameter beta I will not be significant? What would you like to see in that interval for that parameter not to be significant? 0. So if this interval is around 0, right? So it goes for plus minus something, with high probability basically, that parameter will not be significant. So this is another way to do a model selection. So what I suggest is, don't just run the homework, right? Look at these things and try to compare different criteria and just comment on how useful these type of things are about. Now, in the early part of the lecture on Tuesday, I gave you some non-Bayesian confidence intervals. Didn't tell you how they're computed. They're actually motivated by p-values and things like that we didn't elaborate at all since that is not the emphasis of the course. But let me just say, this confidence interval does not coincide with the non-Bayesian confidence intervals. They're not the same. Okay? There is, there is another prior that we're going to introduce shortly that somehow by miracle gives you the same answers for these HPD intervals as the frequentist confidence intervals. But these particular ones don't coincide. Not only they don't coincide, the meaning of this is completely different from the meaning of that people assign to these confidence intervals in the non-Bayesian world. All right? So actually, this is, I wasn't expecting this slide to be here, right? So the confidence intervals you get from the frequentist perspective, they look like that, okay? So if you compare basically the two slides, you will see they are not the same, okay? I mean, they have, visually they look the same, they are very different, okay? And not only they are very different, the interpretation again is different because this comes from the p-values world, the other one comes from the definition basically of these high probability density intervals. Okay, so I need to calculate, since we talk about Bayes factors, right? Somebody will ask, okay, you told us all the posteriors of all the parameters, the marginals, you told us how to do predictions. How about the marginal likelihood? Because the Bayes factor requires that you know the marginal likelihood, okay? How about the marginal likelihood? So let's see what's going on here. So the, let's see how we're going to, so can you remind me the formula? Don't look at this on any of this, right? in a Bayesian setting, how do you calculate the marginal likelihood? Remember, the marginal likelihood basically is what appears on the denominator of Bayes' rule. And it's an integral of what? It's a normalizing factor in the Bayes' rule, and it's an integral of the likelihood times the likelihood, here we have to be very careful, times the prior. Okay? It's very important. So the normalizing factor is basically an integral over the parameter space, right, of the likelihood times the prior. Okay? So let me see what I have done here, all right? So I am trying to avoid all calculations and see only the essential things here. Okay, so so can you recognize? So here you notice I have not involved the parameters beta, all right, because I'm going to use equations where the integration in beta already has been done. Okay, so can you recognize somewhere here the likelihood? Which of all of in here, which term do you think is the likelihood? So, since this integral, right, is supposed to involve an integration in beta, but I already have integrated beta out in the way that I'm going to calculate. So when I say likelihood times the prior, I'm only going to use the prior on sigma square because beta I'm going to integrate it completely out. So when I do predictions on the likelihood, I am going to do predictions where beta has been integrated out to make my life easy. So this is sort of a marginal likelihood given sigma squared, but it's marginal because beta has been integrated out. Okay, so I'm going to come back to how I get this formula, but if this is the likelihood with beta integrated out, so effectively what you have is, it's an integral of this likelihood, this Gaussian, all right, which is all of these terms, times the prior in sigma squared, which is 1 over sigma squared, which is this minus here. This comes from the Gaussian, all right, this comes from the Gaussian. This comes from the prior, so this is what this integral looks like. And the final answer, it's actually, I'm going to simplify it, is what you see here. If you do the integration on sigma squared exactly, you get basically this big parenthesis, the minus n over 2. So the question I have to tell you is, how do you get this formula? This is the marginal likelihood where the marginalization is only on beta. So look at the derivations and tell me from where is this coming. You remember what is when you look at the likelihood, right? The likelihood is what? It's if you write it in an exact form, is y equal x times beta plus the Gaussian noise. So the mean is really x times beta, but if beta follows this distribution, you remember we just, this is the prior, all right? If beta follows this, x beta follows that, and then to get y, the only thing you have to do is add the noise sigma squared times I. If you don't like, again, this derivation, you can go and look at the previous slides where I basically had integrated W explicitly, or you can do your own calculations and see this directly. The way that I look at it is y is equal to x times beta plus the noise, which is Gaussian sigma squared variance. And because beta follows a Gaussian, x beta follows a Gaussian with transformation of the mean and the variance. So the marginal of y with marginalization only in beta follows this. So I plug it in, I put the prior on sigma squared, which is 1 over sigma squared, I get that. I integrate, and the marginal likelihood takes this wonderful formula on the bottom, okay? That looks painful because I told you computing marginal likelihoods, it's a very complicated calculation in general. Okay, that's why lots of people don't do it unless they discuss model selection. So before I show you the this formula here, in case it's simplified, notice that I am conditioning it on C, because I want to do some nice tricks about C. The idea here is, C was coming in our prior model, so I am putting it there as a parameter that we really don't know what to use, okay? So the marginal likelihood for a given C is given like this, and you don't need to know this is the magic thing, okay? Where actually do I need these calculations? Give me 1 second. Well, let me ask you something. Right now, my brain is functioning, is back. The fact that I put a blue color there means I had to remind you that that term is not trivial. There is some substance there. So can you tell me? So you remember, this calculation involves this Gaussian, right, times the prior 1 over sigma squared and integral over sigma squared. So where did this term come from? Just look carefully and tell me. 1 over c plus 1 to a power k plus 1 divided by 2. Just try to imagine from where is that term coming. Obviously it's not coming from the prior, it has to come from the likelihood. So where did this term come from in the likelihood? I mean, the mathematics are not important, right? But, how do you write a Gaussian explicitly? You have the exponential term, which is this, and then you will have 1 over 2 pi to n over 2, and then what else on the denominator? 1 over square root of what? 1 over square root of? This is a multivariate Gaussian. I mean, if it was univariate Gaussian, you put the sigma squared to a half. What do you put here for a multivariate Gaussian in the denominator? 1 over the square root of? The determinant. So somehow we're going to need the square root, which is 2, and we will need the determinant of this huge animal there, I plus c times all of these things. And it comes out that this determinant is c plus 1 to the power k plus 1. And it is not obvious actually that the determinant is that, but the next 2 slides prove that. Okay? And you can prove it on your own way, right? But this calculation looks, trying to calculate this looks complicated, but if you think about it, right, there is some structure there. And that structure at the end of the day gives you 1 over c plus 1 to k plus 1. Okay? So the derivation, again, it's in the notes. So you can read about it. All right. So what we have done is, for a given c, we calculated the marginal likelihood. Okay? And this is what we need in Bayes factors. So in Bayes factors, actually what we will do is, let's say we take coefficient beta 1. So we will calculate the marginal likelihood where all the variables are in, and this will be our calculation, right? So all the variables are in, we use this calculation, and then we will repeat this calculation where all the variables but beta 1 is out. So x1 is not accounted for. So without having to bother you with the notations, right? Can you imagine when you want to use this in the case where the variable x1 is not accounted? What changes will you need to do in this formula? I mean, look at this formula, and if you want to write it to calculate the marginal likelihood for a model where you keep all the variables but x1, what changes will you go and do on this formula? I mean, some of the changes. Can you tell me, like, are you going to change, are you going to use capital X, the whole thing, as input? So what will you do to capital X? So you don't want variable x1 in the model. So what will you do to capital X? Remember, actually, each column corresponds to each input. So what will you do to input, let's say, x1? Remove it out. One line command in MATLAB or Python or in R, all right? You just take that column and you remove it out, okay? So let me just give you, and again, I'm not going to bother you with the notation because it doesn't really mean anything. So here is so let me just, okay, I said I'm not going to say anything about the notation. So let's call here H0 the model where we have removed, let's say, variable beta 1. That's our hypothesis, right? And I am writing this in a much more general sense where I can remove multiple variables at the same time. So H0, I remove variable 1. So you notice on the marginal likelihood, the only thing I have to do is effectively, use x0, use beta 0, and everything else basically is the same. Okay, it's exactly the same formula as before. Okay, and so here Q, all right, corresponds to the number of variables that I remove. In my case, if I remove only one, Q will be equal to 1. Okay, so I'm removing one variable out. Okay, so how do you compute the biggest factors? I'm using different Cs basically here just to generalize this. So for the full model, I use C. For these, when I remove one of these input variables, I use C0. So if you remember, the marginal likelihood is this big bracket to -1/2. So the -1/2, so the full marginal likelihood, then it would become this denominator to n/2, right? Remember, it was -n/2, and this will become this term here, because it's 1/that to the power n/2. So effectively, in your computer program, you will select basically the variables that you keep, right? These are the coefficients that you have computed. These are the elements basically from the prior mean. This is from the input. You exclude basically the rows that you're interested. You do this calculation, one line to the power n/2, and that's the biggest factor. So when you look at the MATLAB or Python program, literally you will see this calculation running over, what happened? Okay, so this calculation running over 2 lines, but basically this is what you need to put in. And I advise you to actually convince yourselves that this derivation is correct, and really what you put in the program is all of these terms carefully, okay? And you notice here, if you exclude, let's say, input j, this is the command that you define x0 in MATLAB, one line. You say take the given x, vector, remove basically the column j, and that's x0, and you basically override the previous formulas to compute the marginal likelihood, and this is the biggest factor. Now, you notice here that, so again, I use different Cs for the two models, but there is a dependence on C, all right? So we're not quite sure if this Zellner's informative G prior, if actually is a good one yet, okay? So I'm going to come back to this Zellner's G prior, all right? But let me just push this to an informative limit in 1 or 2 slides and give you a new prior for both beta and sigma squared. The whole prior looks like that. You remember all the priors that we discussed up to now is a normal distribution of beta given sigma squared, and then some either inverse gamma or 1 over sigma squared for sigma squared. Here, I take a uniform prior on beta, and 1 over sigma squared basically is f is prior for sigma squared. So if you repeat all the calculations we did, all right, you come up with very simplified formulas, some nice estimates, Bayes estimates for the mean, and nice marginal posteriors, all given by nice formulas. And the only thing that I wanted to emphasize is that if you use this prior, that somehow by a miracle of nature, these high probability density intervals that you get coincide with the frequentist confidence intervals. I mean, you literally get the same numbers. The only difference is the frequentist confidence intervals have nothing to do with anything of this analysis. So it's like a miracle that they come to be the same. They come from completely different perspective, but somehow this choice of prior gives you those answers. So if I remember, in one of the calculations in your homework, you have to calculate this high probability density intervals for this the regression coefficients, and you see them here. And I can tell you, for using this prior here, all right, using this prior, somehow the formulas will be the same, identical as these frequentist estimates, and this is what has been used here. By the way, I asked one of the TAs who is preparing work on this homework to confirm that, and I forgot my microphone, hopefully something picks me up here. It's okay, you can hear me. So it comes out that I want to be sure that in the homework, it basically tells you to compute this HPD intervals for this prior, okay? Because in the program that we gave you, this is what is being used, okay? Not the other formulas that I gave you 5 minutes earlier. So just double check that basically is asking you this under the correct prior. All right. So let's make life complicated now. I'm going to go back to this Zellner's G prior, and we notice when you calculate the Bayes factors, there is still an effect of this C, all right? And C was coming in the prior for the coefficients, okay? So we need to do something about C. And what we are going to do is we're going to assume that C is a random variable, and we're going to average over all possible C's. So we're going to do a Bayesian model averaging. So, you know, if there is an effect of C, how about if we take all the possible models for all possible values of C and average them out, okay? So to do that, first I'm going to simplify things. I'm going to take that the mean of the prior is 0, just to make, I don't think the formulas will be affected much because you can use the previous results, but I'm going to take this to be 0, and I'm going to take as a prior of C to be 1 over C, okay? And I'm going to take C to be an integer here, okay? So just so the calculations from integrals basically will become summations over integers. So what we need to do is we need to find the posterior now. So if C is going to be integrated out, right? So when you find the posterior of beta and sigma square, you're not going to condition your results and keep sigma there. You're going to integrate C completely out. So look at this formula. Does it make sense to you? All right. So basically, what is like what I have done here is like put before, right? If C is going to be a random variable, I'm going to write this as an integral of the probability of beta, sigma squared, and C, given my data, integral in C, and then I'm going to write this as this conditional given C times the posterior of C. And it sounds weird that C became a coefficient, now there is a posterior of C. So we will see what that means, right? Is this result known to us? Do we know the posterior, the joint posterior of the parameters and sigma squared if we knew the data and C? That's not what we did before. So this is known, okay? So now what is unknown is this posterior of C given the data. So I can write this as the likelihood. So what's the likelihood of Y if I knew C, all right, times the prior of C, divided by this normalization factor, okay? And right now we don't care about the normalization factor, okay? So the prior of C is 1 over C, and this is what I have. And let me ask you, can we compute the marginal distribution if we knew C? Do we have any formulas from what I did 5 minutes ago to compute the marginal distribution of Y if we knew C? You remember? You want me to go back 2 slides? 3 slides? Here, this slide. How about this? Come on. How about this one? Right? So if I knew C, the marginal distribution of Y is no. Okay? So, I don't know how to advance this. Okay, so let's, all right. So we know this, we know this, we know that. To compute then this posterior, we have to perform this this summation here. Okay. So all right. So this is the formula. Actually, I did not know it was given. Okay. So this is given C. This is how the marginal likelihood. This is how the likelihood looks like. Okay. It's the marginal likelihood. All of the parameters have been integrated out. Right. So if you simplify this and you take the prior mean to be 0, this formula looks even simpler. All right, looks like this. What actually you can do is, you can compute not only we can do this calculation, right? But you remember we will need to compute the posterior of beta given sigma squared. And we will need to compute the posterior of sigma squared, the posterior of beta, where in all calculations, the coefficient C has been integrated out now. Because before we had these things with the coefficient C, now we're going to integrate this thing out. So how do we do this, okay? So, if I remind you from the previous calculations, for example, if you look at the marginal distribution of beta, given C, looks like this, all right? So now we want to find the distribution beta follows, all right, with C integrated out. And I'm going to use my standard trick. I am going to compute the mean of that distribution and the variance of that distribution by conditioning on C. So I'm going to say the mean of that distribution for C is integrated out. It's actually the expectation with respect to what variable? C of the expectation of beta condition on C. And that expectation is basically this quantity here, right? This is the mean. So when I take this expectation, basically what do I get? Let me go directly to the formula. I get the MLE estimate, and then I have to compute the expectation of C divided by C plus 1. So look at this formula and tell me where the ratio of the two summations came. So this means I have to compute the expectation of C divided by C plus 1 with respect to the posterior of C. Right? Because you notice here this condition on the data, the posterior of C. And you remember the posterior of C, I told you it was proportional to what? It's here. What is the posterior of C? Is this likelihood times the prior. So tell me how from this integral I go to this calculation. So beta hat comes outside. What am I doing here? How do you find the expectation of some random variable? A discrete random variable. What's the definition of the expectation of a discrete random variable? Is the sum of the variable times what? The probability. right? And what I have done here, this is the probability involving this marginal likelihood times the prior, and what do I have on the denominator? I have the marginalization term. All right? So basically what this formula we already know, this we already know. Effectively, we have the posterior mean and similarly the posterior variance of beta without any C on it. C has been integrated out. Okay? And so here I am giving you, for example, similar formulas for the posterior mean of sigma squared with C integrated out. It takes a nice formula. And, again, so if you want to write the distribution, it's a student t distribution. You know the mean, you know the variance. And effectively, these are Monte Carlo estimates of the mean and the variance, right? That's what they are. And they're facilitated from the fact that C is a discrete random variable. And if you want the marginal likelihood without any C there, is basically that was what we had in the denominator, what I showed you before, is basically this summation here. And you can show actually, and I think when you play with a computer program, that actually this summation converges very nicely. So it's not sort of a divergent term or anything like that. It actually converges. Okay? So, so one of the calculations you will run basically, and it's in the computer program, will be to compute this posterior means and the error bars, the variance of the parameters, where you have completely average over all possible values of C. And the formulas basically use this. The ones derived in the earlier slides, you can see this is the expectation of the posterior of beta, okay, and the variance of beta, and these are the calculations you get. So now, literally, okay, so this is not needed here since the summation is C, so this is obviously a typo, right? So this is with beta, curly beta in the prior being equal to 0, all right? And this is what you get. And you can actually, for this case, you can repeat the calculation of Bayes factors and effectively integrating this C constant out. And effectively what you need is, you need these formulas for the marginal likelihood with the integration in C. So in fact, effectively what you can see is, this is what we had before, and you see the prior there, 1 over C. Right? There is really nothing particular to this. And the formulas basically gives you nicer results now, okay? So this is correct, there's no C here, and you can see these Bayes factors. And somehow, again, the results give you very strong evidence that the intercept, variable 1 and 2 need to be there, 4 and 5 need to be there, but somehow all the different types of approximations, they point to the fact that variable number 3 is not very essential. Okay? Variable number 3 is not very essential. And of course, the rest of the variables are really not needed in the regression model. Maybe actually one of the things that you can do is, right, you can run this model and literally remove multiple of these variables out and see what happens. Do you actually get similar results or not? Okay, so you can, if you want, you can try something like that. All right. So I am done basically with regressions and priors, and I will continue with regression for the rest of the lecture, but I want to do something that is not very difficult to discuss it, but it's sort of a little bit ahead of us because it requires some ideas of Gibbs sampling, okay? And we haven't done anything about Monte Carlo methods yet, but the concept is so simple, I'm gonna throw it. Hopefully you will appreciate it, and you will appreciate the significance of using these sampling methods for doing model selection in a regression. So basically we will try to get some other alternative method for computing which variables are important, okay? Because somehow, if you have, let's say 11 variables, right? And you try to figure out all possible, if you try to examine all possible combinations that will give you different models. You know how many models you will come up if you say, I keep this variable, I don't keep it, I keep that variable, I don't keep it. How many total models do you think you will have for 11 variables? How many total models may come out of this analysis that somebody will need to consider? Remember, each variable is in or out. So how many total models I have? 2 to the power 11. All right? So basically, if you try to compute these posteriors and these error bars on beta for 2 to the power 11, your computer will crash. And I believe in your homework, the program actually is doing that. That's why I told you to plug in your laptop at night while it does the calculation. It goes through all possible models. So what we would like to do is we would like to investigate a method where rather than doing the calculations for every model, can we actually start doing calculations for the most probable models? And the most probable models means we're going to have to sort of start sampling from this model. We need to figure out which are the most probable models. So this is what I want to discuss, all right? So we cannot do 2 to the k models. So we're going to have to do something a little bit smarter. So first assumption I'm going to make is that, that somehow you can build these regression models using any combination of q variables. So I can use variable 1, 2, and 11, or 1, 3, and 10. So any combination of I1 to IQ for q less than k will be an acceptable sort of regression model. Some notations. For each variable, we're going to introduce an index gamma, an indicator that says, yes, I am in the model, no, I am not in the model. All right? And we're going to define the total number of inputs that are in the model as the vector 1 transpose times gamma. You agree? So gamma will be a vector of 1s and 0s. So 1 transpose gamma will tell me how many variables are in the model, if I knew gamma. Okay? And 2 variables that I'm going to introduce is T1 of gamma will be the set of the indices of the variables that are in the model, and T0 of the variables that they are not in the model. I'm going to show you this when you see the analysis shortly. So, for example, if I use a model beta gamma, right, this will consist from the intercept variable beta 0, so this is the coefficient, the regression coefficient for the bias, and then the parameters beta I, where I belongs to T1 of gamma. If, I'm defining a model gamma, right? A model gamma means I have decided which variables are in and which are out, which means I have decided what T1 gamma is. So if the index I belongs to T1 of gamma, then I keep these variables beta I, the rest are not there. So this can be, if T1 is variable 1, 3, and 10, so this will be beta 1, beta 3, beta 10. Okay? This is a compact notation, so beta gamma means it's a vector of the coefficients beta for all variables that have gamma equal to 1. For all variables that they are in the model. Right? Okay? So we're going to define, so we're going to call this model model M gamma, all right? And somehow all the formulas that we have used for everything we have done today and on Tuesday and the previous lectures, right? Is like conditioning on gamma. If I know what variables are in, I can do any calculation. So for example, do you think, is this a good calculation for the likelihood? Look at this and tell me if there's anything weird here. Is this a good calculation for the likelihood? So the likelihood you're conditioning on beta and sigma squared and the input, right? But now I condition it not on beta gamma, because I already have gamma there in the conditioning. So for a given gamma, there is a set of parameters beta gamma. I forgot to tell you I'm going to take the same noise for all models, right? It will be difficult to do something different, but you guys can think something better. So the likelihood, given the parameters, is basically x gamma, beta gamma, and sigma squared I for the noise. Okay? So effectively what I'm trying to say is all the formulas that we had before, if you add the subscript gamma there, that identifies which variables are there and which are not, they are the same formulas as before. All right? They're exactly the same formulas as before. All right? We're going to introduce this Zellner G prior, and we're going to, this is, I just remind you what the Zellner G prior was that we considered today, all right? So some prior, it's a Gaussian for beta given sigma square. This is for the full model. But I'm going to rewrite this equation on the top. I'm going to rewrite it for the model M gamma. So please look carefully here and tell me that really you understand how from there we go there. You notice this I condition on gamma. So it's like running a regression problem where your variables are not all your variables that you get there, but a subset of variables. For that subset, obviously, there is a beta gamma, there is an x gamma that you kept the appropriate columns. The formula is the same. Right? The formula is the same. And you notice here, we're conditioning on gamma. So if we knew gamma, all right? We don't know gamma. If we knew gamma. So if we have a given model, right, this is what the situation will be. All right? So for example, if I take the prior, the joint prior, right, I can write this as the 1 over sigma squared that we had before, and the Gaussian for beta gamma. And Q gamma here is what? Is, what's Q gamma in this model? Is the number of parameters in the model gamma, okay? And it is +1 because we always include the bias term. Right? So you have Q gamma variables x1 to x11, let's say in our regression problem, you select which ones the model includes, +1 for the bias, so we have Q gamma +1. All right. I am going to, there are not going to be lots of formulas, right? I'm going to review some of the results, and then I am going to tell you how actually you can start doing magic, going from one model to another, using this concept of Gibbs sampling. So let's first look, we're going to compute, this is a new concept, we're going to compute the posterior over models. You remember somewhere I had thrown this when we were discussing about model selection, right? So this is the posterior of gamma given my data. A new concept, what does that mean? You know what? This probability, think of it, is like the probability that tells you which selection of the gamma variables best explains the data. Right? What model best explains the data? So how do we write this? This is the likelihood, all right? With these variables, there's no other parameters here, times the prior, all right? So this posterior is really proportional. It's proportional to the marginal likelihood, right, that we know how to compute for a given gamma, okay? And if you want this calculation, okay, we already did this before, all right? So the posterior is proportional to the marginal likelihood, and I'm just giving you the formula here for the marginal likelihood, okay? This is what we wrote before. The only difference here is, instead of having x, I have x gamma. Instead of having curly beta, I have curly beta gamma, and the rest is the same. It's the same formula as before, right? I'm restraining this for model gamma, and this is what I have. Okay? So the posterior is proportional to the marginal likelihood. This is what we need to use. Okay? So again, this is a nice way to write, this posterior, and I am not going to integrate C out on this model, so I'm going to keep things simple. So I'm going to keep C, and I'm going to choose some value of C to do the analysis. But this is the posterior, right? That is given by this nice formula. All right. So what can you do if you have the posterior? if you run the previous programs, right, for the prior, the Zellner prior, actually, if you run that program and you finish training it, you can go and plug in all these values as they are for every possible choice of gamma, all right? For every possible choice of gamma, so for all models, you can plug in this and you compute the posterior, and this is what you get for the posterior over models. It's a new concept. So on the left, what do I have? What do you think I have on the left? These are each of the rows corresponds to a different model. So row 1 is the model that involves the bias, the first term, the second, the fourth, and the fifth. And what's the posterior probability of that? 0.23. What is this model that involves the bias, variable 1, 2, 3, and 9, and what's the posterior of that? So immediately you can see that the most probable model that explains the data is the model that involves variables 1, 2, 4, and 5. Surprisingly, variable 3 is not there. And you remember all the indicators, Bayes factors, confidence intervals, are indicating that variable 3 is not very important. You notice now, variable 3 is not anywhere. Okay, it's coming down there with very low probability. Now, to get this table, what I really had to go is say, go through all the models and repeat this calculation, right? And it's a straightforward calculation, but it's 2 to the power 11. So lots of models, no good. So what we want to do is, we really want to do something smarter, okay? So I'm going to tell you what that smarter calculation is going to be. By the way, you can integrate C out also as well, okay? I mean, I don't have to go through the details, but you can calculate C out, and the results basically, this is what you get. And again, model 1, 2, 4, 5 is the most probable model. So I want to tell you a smart way without having to compute all these models, and that smart way, and we will learn this in the rest of the course, would be to use ideas from Monte Carlo methods, and particularly Gibbs sampling. So the idea is, these sampling methods, right, somehow they will allow us to start taking, generating samples from the posterior, let's say, of gamma, okay? And those samples, after a while, they will become independent of each other, and we can use them for Monte Carlo type of calculations, all right? So this Gibbs sampling, basically, methodology, the algorithm is what you see here. If you want to build an algorithm, which is here the Gibbs sampling algorithm, to generate samples that come from the posterior of gamma, here is what you need to do. You need to sequentially start generating samples of gamma 1 only, of gamma 2, and gamma k. And what is, from where do you sample gamma 1? You sample it from the conditional posterior of gamma 1, where all the other gammas are fixed. What that means is, right, with given values of the gamma 2 to gamma 11, so with already decision if the variables x2 to x11 are in or out, okay, you sample from the condition of gamma 1, given those variables and the data, okay? Now, and to what values do you fix the previous variable? How do you know if they're in or out? Since you're going to do it iteratively, you're going to use whatever calculation you decided before. If you decided they are in, you keep them in. If you decided they're out, you keep them out. So the syntax T that you see here indicates an iteration. Okay? And so this, then you sample gamma 2 from the conditional distribution of gamma 2 given the previous gammas. Okay? And now you're going to say, yeah, but now life is more complicated. You told us to compute the posterior of the whole gamma, and now I have the marginals, I have the conditionals of each gamma. So if I give you this posterior of the whole vector gamma, can you compute each of these posteriors, or how are you going to compute them? So if I give you, again, the posterior of the whole gamma vector, gamma 1 to gamma k, how do you calculate this condition of gamma 1 given the other gammas? What is the trivial thing you can do? If I give you the joint posterior and you want only the posterior of gamma 1 given the other variables, what do? You use the joint posterior, and then what values do you plug in for the other variables? The fixed values that you want to condition on. Okay? So the idea is basically to compute, let's say, the conditional probability of gamma 1 given the other gammas. Effectively, what you do is take the joint, all right, fix the other gammas, all right, and then calculate this joint for gamma 1 equal to 0, which means variable gamma 1 is not in, and gamma 1 equal to 1, which means variable 1 is in. Okay? So, and do we know the joint posterior of gamma? Yes, because I showed you the calculation before, is proportional to the marginal likelihood. Basically, we have a closed form solution for this probability. So the idea here is this Gibbs algorithm allows us to iteratively calculate samples of gamma 1 and gamma 2 and gamma k, all right? And when you iterate this, after a number of iterations, can be maybe hundreds of iterations or thousands, the samples that you will get will be actually samples, let's say, from the posterior of the joint distribution of gamma 1, gamma 2, gamma k. Which means, if you actually use the samples to do Monte Carlo estimates, you can see how many times the variable 1 was on. That will give you actually the posterior of the variable 1. Then how many times the variable 2 is on, that's the posterior of the variable 2. So effectively what we can do is, rather than going and testing all the models, we can use a Monte Carlo estimate, all right, to calculate how many times these variables gamma 2 give us a combination of, let's say, of some gamma variables, all right, and that will be the posterior of gamma. Now, so T is the number of samples that I am using, or iterations in the Gibbs sampling, and what I indicate here is, when you run this type of algorithms for sampling, you can only trust them after a number of iterations. So you run them for, let's say, 1,000 times, you don't pay any attention to the samples you collected in 1,000 times, and only after 1,000 times, you start collecting to do this calculation. Okay? Because sort of you want to get rid of whatever effect your starting point has on this Markov chain, as we will see. Okay? So what happens when you implement this algorithm? Extremely fast. So this is the calculation that we did before, right? For different models, you go, you plug in your gamma variables, this is what you get. And this is actually the estimates you get with Gibbs sampling. You notice the results basically coincide to 2 decimal digits. The cost of doing Gibbs sampling to do this is infinitesimal versus the cost doing this for sort of all possible models. And all possible models here is 2 to the power 11, but you can think on a real problem where you have 100 variables. 2 to the power 100 is a big number, isn't it? Okay, so with Gibbs sampling, the idea is you start taking samples of these gammas, and as you progress, the samples will be towards the mode of the posterior of gamma, right? You'll be sampling the most probable models, right? And this is actually what you see here. Okay? So 2 completely different ways to do these calculations. The painful way, where explicitly you collect all the information for all possible models. I mean, if somebody doesn't give you this, right, you really have no other chance but to enumerate everything, write down, compute this probabilities. Here, effectively, you let the whole thing run, and you say, just tell me what's the most probable model, and there it is, 0, 1, 2, 4, 5. Very nice, okay? Very nice. And again, you can do these calculations where, You have the informative Zellner's prior, or you integrate C out and you have the uninformative. You can do actually anything you want to, and you can actually use this in your own research if you need to do high dimensional linear regression problems. Okay? So, and if you want, again, for individual models, if you want to find the probability of, these are marginal probabilities, right, of gamma I to be equal to 1, you can see this probability of gamma 1 being on is very high, this is very high, this is very high, this is very high again. This probability for gamma 3 is lower, all right? And even probability of gamma 6 is higher than gamma 3, and this again is consistent with sort of all the calculations we have done before. Okay, so I am done with this. So really what I need to do something very trivial tomorrow that is going to be a very short lecture. I want to, you remember when we started talking about regression models, we started with some simple priors, and then I said, let's take the parameters of the prior as constant now, and we'll deal later. So tomorrow what I want to tell you is how we apply this hierarchical Bayes idea to compute hyperparameters basically in prior models, okay? And that will lead sort of to the idea of this what's called maximizing the model evidence, all right? And it will be, it's a very nice example that comes with a nice computer program that I want you to see it, because effectively it eliminates the need to think that somehow you have to go and fine-tune parameters. No, you don't have to fine-tune. If you can do it smartly, you can either integrate those parameters out the way we did with C, or actually what you can do is you can put a prior on the things you don't know, and then somehow use the evidence approximation to fix the hyperparameters that you have in your model. So we will do this on Tuesday. I haven't decided what is going to be happening on Monday, because I'm out on Tuesday, because I'm going to be out of town. So I will let you know tomorrow. In case I forget, let me know, remind me to see if we're going to have the TA to do the homework or not. Okay? So I will see you tomorrow.
Oh,